Stoichiometry is a very important concept in chemistry that allows us to use mole ratios from the balanced chemical equation to quantify the amount of reactants and products involved in a chemical reaction. But what do we mean by mole ratios? Well, let's look at this reaction where nitrogen and hydrogen combine to form NH3 ammonia. We can see from the balanced chemical equation that 1N2 combines with 3H2 to form 2NH3. And these coefficients, 1, 3, and 2, can be viewed in several different ways. The simplest way is if we were to consume 1 molecule of N2, it would require 3 molecules of H2, and then we would produce 2 molecules of NH3. But in any real reaction, we would never have such few molecules. But this ratio remains the same. For example, let's assume we had 250 nitrogen molecules. Well, then that would require 750 hydrogen molecules to be consumed in the reaction, and it would result in the production of 500 NH3 ammonia molecules. In both situations, we see that there's a ratio of 1N2 to 3H2 to 2NH3 in the reaction. Take a moment to fill in the last 2 rows of this table to see if you can follow the pattern of this reaction. If we look here and we see, what if we had Avogadro's number of N2 molecules, or 1 mole? Well, then it would require 1.81 times 10 to the 24th H2 molecules, or 3 mole. And it would produce 1.20 times 10 to the 24th NH3 molecules, or 2 moles. Same thing down below. If we had 4 moles of nitrogen, we would require 12 moles of H2, and it would result in the production of 8 moles of NH3. Every time the reaction happens, it happens in a 1 to 3 to 2 ratio. These are what we mean by mole ratios. The stoichiometric coefficients in the balanced chemical equation show the proportional amounts of each species needed for the chemical reaction. This ratio of the stoichiometric coefficients, the coefficients from the balanced chemical equation, we call this the mole ratio. In a chemical reaction, reactants always react in the relative proportions equal to this mole ratio. So we will always have a 1 to 3 ratio of nitrogen to hydrogen. Regardless of the amount of material actually reacting, it'll always follow that 1 to 3 ratio. And the products will always form in the ratio dictated by the chemical equation as well. So we will always produce 2 NH3 for every 1 N2 and 2 NH3 for every 3 H2. So knowing these mole ratios allow us to quantify how much material will be consumed in a reaction and how much material will be produced in a reaction. Now let's try to apply this concept of the mole ratio. So let's use the mole ratios from the balanced chemical equation above, where 1N2 reacts with 3H2 to produce 2NH3 to solve the following problems. We're going to use dimensional analysis for each of these. So the first question is, how many moles of nitrogen would be needed to make 10 moles of ammonia? Pause the video and try to solve this using dimensional analysis. Well, if we're starting with 10 moles of our product, NH3, and we want to know how much of the nitrogen must have been consumed, we need some ratio of moles of NH3 to moles of N2. And we can see from the balanced chemical equation that it's 2 moles of NH3 for every 1 mole of N2. So that's what fills into our conversion ratio. Our mole ratio allows us to convert between moles of NH3 product and moles of the N2 reactant. And now we can calculate our final answer to be 5 moles of N2 consumed in the reaction. If instead we want to know how many moles of ammonia could be made if we completely react 9 moles of hydrogen, we're going to start with our 9 moles of H2, and again use the balanced chemical equation to get our mole ratios for a mole of H2 consumed for every mole of NH3 produced. And we're going to see that the ratio of H2 to NH3 in the reaction is 3 to 2 because of the balanced chemical equation coefficients before those species. And this will result in 6 moles of NH3 being produced. Here we have some more practice. In the space below, write the balanced chemical equation for the complete combustion of propane, which is C3H8. And then what I want you to do is I want you to assume that a student reacts 2.25 moles of that propane according to the reaction. And I want you to find out how many moles of oxygen gas would have to be consumed in the reaction and how many moles of water vapor would be produced in the reaction. Show your work using dimensional analysis for both. I'll give you a second and then I'll fill in the answer. So the balanced chemical equation says 1 mole of propane will react with 5 moles of oxygen to produce 3 moles of CO2 and 4 moles of H2O. So using those coefficients from the balanced chemical equation, we can see that if we're going to react 2.25 mole of propane, CH3, for every 1 mole of propane reacted, you would consume 5 moles of O2. So our final answer would be 11.3 mole of O2. And in question 2, we can see that because there's a 1 to 4 ratio of moles of propane to water produced, there'll be 9 moles of water produced if we use 2.25 moles of propane in the reaction. Now in this next problem, we're going to do a slightly more challenging extension of what we've been doing. In this situation, we're told that a student reacts 3.50 grams of propane, C3H8, according to the combustion reaction above. But in these balanced chemical equations, these coefficients represent mole ratios, not grams or mass ratios. So the first step in any stoichiometry problem where you're provided anything other than moles is to go to moles first. Then you can use your mole ratio. So anytime we need to know the number of moles from the mass in grams, we just simply use the molar mass from the periodic table. And now that we have moles of propane, we can solve our answer to find how many moles of carbon dioxide would be produced by using the coefficients from the balanced chemical equation as a mole ratio. And we see that this reaction would produce 0.236 mole of CO2. Notice that just like all other dimensional analysis, all of our units cancel out such that we are only left with the unit of what we're trying to solve for. Take a moment to try number 4 on your own, and then I'll show you the answer. Well, this problem was a lot like the one above, where we had to start with our mass of propane, use the molar mass of propane from the periodic table to get to moles of propane, and then use the mole ratio of propane to oxygen in the balanced chemical equation to get to oxygen. However, we had to add one little wrinkle extra, which you see here in green, and this is the last step of stoichiometry. The last thing you do after you go to moles, then use the mole ratio, then you go to whatever you want. And since we wanted mass of oxygen in this situation, we had to use the molar mass of oxygen from the periodic table. And we find our answer is 12.7 grams of oxygen. Okay, now let's try to finish out some practice. In this first problem, we're asking you how many grams of aluminum metal would be consumed in a single replacement reaction with 3.00 moles of aqueous copper 2 chloride. Write the balanced chemical equation and show your work. I'll show you the answer in a second. So here we find that the answer to this first problem was 54.0 grams of aluminum. If you didn't get that correct, make sure you're checking your balanced chemical equation to make sure all your chemical species are correct and your coefficients are correct. You should have started with moles, then used the mole ratio to go from moles of copper 2 chloride to moles of aluminum, and then use the molar mass of aluminum to find grams of aluminum. Give each of these 3 problems a try on your own, and then I'll be right back with the answers. Okay, in this first reaction, we have the same reaction as before, but this time we have 2.50 moles of copper 2 chloride, and we're asked to find the grams of copper that would be produced in the reaction. Again, we do mole ratio to go from moles of copper 2 chloride to moles of copper. Then we use the molar mass of copper to go from moles of copper to grams of copper, and our final answer to 3 sig figs is 159. In this next reaction, we had a neutralization reaction, double replacement neutralization, where we have an acid and a base making water and an ionic aqueous salt. And we were given grams of the sulfuric acid to start with, and we wanted to find out grams of the water, which the answer was 1.14 grams. Because we started with grams, the first thing we had to use is this green conversion here, which is the molar mass of the sulfuric acid, to go from grams of sulfuric acid to mole of sulfuric acid. Then the blue numbers is going to be the mole ratio, where we go from moles of sulfuric acid to moles of what we want, water, HOH or H2O. And then lastly, we had to use the molar mass of water from the periodic table to get to our final answer of 1.14 grams of water. And in the last reaction, we have solid aluminum combining with iodine to make aluminum iodide solid. This is actually the reaction we saw that made the purple powder, purple smoke, and we're told that if we produce 4.50 grams of the aluminum iodide in the reaction, how many grams of iodine must have reacted? And so if we look here, we're going to start with grams of aluminum iodide, then always go to mole first. So we're going to use the molar mass of aluminum iodide to get to mole of aluminum iodide. We're going to use the mole ratio from the balanced chemical equation of 2 to 3. So every 2 moles of aluminum iodide will react with 3 moles of iodine. And then lastly, we're going to use the molar mass of iodine, which is I2. It's a diatomic. It's one of our Hofbrinkels, to find that the mass of iodine that must have reacted was 4.20 grams of iodine. Okay, one more page of practice. Try these 3 on your own, and then I'll be back in a second to show you the answers. Well, in this first reaction, we need to always make sure we're checking our activity series, because this reaction is actually no reaction. So it turns out 0 grams of aluminum will be produced. Remember, if a reaction does not occur, it does not produce any product. In this next problem, we're asked to figure out how many grams of the solid precipitate would form when we have 4.00 grams of lead-2 nitrate combined with an aqueous solution of potassium iodide. Well, we'd have to look at our solubility table, and we'd find that the solid product is going to be lead-2 iodide. So 4 grams of lead-2 nitrate. We use the molar mass of our lead-2 nitrate to get to mole of lead-2 nitrate. Then we use the mole ratio of 1:1 from the balanced chemical equation to know that it's going to take 1 mole of lead-2 nitrate consumed to produce 1 mole of lead-2 iodide. And then we use the molar mass of lead-2 iodide from the periodic table to find that 5.57 grams of lead-2 iodide would be produced. And in this last problem, we have another new little wrinkle. We are given liters of hydrogen gas. We haven't had liters yet, but we know that density allows us to go from volume of a substance to mass of that substance. And then once we have mass of the substance, we can go to moles. So again, the first step is always to go to moles. But getting to moles will be something that you need to use a little bit of your problem solving and prior chemistry knowledge to do. So here I can use the density, where every 1 liter of H2 is 0.0899 grams of H2, and then I can use the molar mass from the periodic table to get to moles of H2. Now we can go through the rest of the problem just like we would. Use the mole ratio to go from mole of H2 to moles of what we want, magnesium that was consumed. And then we can use the molar mass of magnesium to find that every 1 mole of magnesium consumed would be 24.31 grams. So that means that this reaction, if it produced 14.0 liters of hydrogen gas, it must have consumed 15.1 grams of magnesium. We're going to save this section of the notes for a second video. So you're done for the day.